Hey y'all, it's Mrs. Blasky. Today we're going to talk about the first topic of our last unit, Unit 9. So we're going to talk about oxidation reduction reactions and electrochemistry in this unit. So today we're first going to introduce the idea of what oxidation and reduction are and how to recognize and deal with them in balanced equations. So first, what we are often going to refer to as a redox reaction. That's an abbreviation for oxidation and reduction. I don't know why you switch the order, but you do. This is a reaction where the oxidation numbers of the chemicals involved change from what they are as reactants to what they are as products. The reason that these numbers change is because these atoms have transferred electrons in the process of breaking and forming new bonds. So not only are they breaking and forming bonds, but they're actually moving electrons around in that process. So if an atom or an element gains electrons, we say that it has been reduced. If a chemical loses electrons, as it goes from a reactant to product, we say it is oxidized. So one of the silly sort of mnemonic devices to remember this is Leo the lion goes grr. Leo stands for lose electrons oxidized. Grr stands for gain electrons reduced. That's one of the most common ways to remember that. If you look around online, there's some other ways, but I like Leo the lion. It helps me out. So in order to figure out whether you've been oxidized or reduced, we need to be able to assign that chemical an oxidation number. Oxidation numbers are pretty much made up numbers. They are a way that we as scientists can keep track of what's going on with these atoms from the reactant side to the product side. So we're really just more looking for the change in that oxidation number. The number itself doesn't mean a whole heck of a lot. So we have a couple rules for assigning oxidation numbers. Any element hanging out by itself has an oxidation state of 0. So this includes any of our diatomics or any metal or non-metal just hanging out by itself. Oxygen, pretty much 99.9% of the time, has an oxidation number of -2. The only exception is in hydrogen peroxide, where oxygen has an oxidation state of -1. Hydrogen will always be a +1. If we have an ionic compound, the oxidation state is going to be the same as the ionic charge on that compound. So that will also help us out for polyatomic ions. And the sum of the oxidation numbers of all of the atoms should equal the overall charge of the molecule. So in general, the entire molecule has an overall charge of 0. So its oxidation number should also add up to be 0. If we're talking about just a polyatomic ion, then the oxidation number should add up to be the same as the charge on that polyatomic ion. So sometimes we might have to get a little creative to be able to figure out what's going on. We might have to break a compound down into multiple parts to figure out what's going on. So in example 1, we've got several different compounds that are written out for us to be able to identify the oxidation numbers. Now we need to be able to give an oxidation number to every single element. So if we're looking at A here, we're looking at copper, iodine, and oxygen. So we need to be able to assign these all oxidation numbers. So overall, I have no charge on this compound together. So overall, my oxidation number should add up to be 0. I've got a polyatomic ion in here of IO3. Iodate is not always a polyatomic ion that we might remember the charge of, but we can use this to help us figure some other things out. So I've got copper in here, I've got iodine in here, and I've got oxygen in here. So this is how I like to write this out to keep track of everything. You don't need to be quite this organized with it. If you can just look at it and figure things out, that's totally fine. So I've got 1 copper. I'm going to multiply it by its oxidation number and get a value. I've got a total of 2 iodines. I'm going to multiply it by its oxidation number. And then oxygen, I've got a total of 6 oxygens multiplied by its oxidation number. Oxygen almost always has an oxidation state of -2. So I'm going to go ahead and put that in there. All of these results added together should equal 0. Because overall, I don't have a charge. So overall, I should not have an oxidation number either. So 6 times 2 gives me -12. So copper and iodine together should be a +12 to get me to 0. To make things a little bit easier, I'm going to help you out. Iodate is a -1, just like chlorate and bromate and all those other 8s. So if iodate overall has a -1 charge, I've got 2 of them. That means copper ionically has a +2 charge. When in doubt, we're going to steal that ionic charge over to be its oxidation state also. So 1 times +2 gives me +2. So if I look at this, 2 plus something -12 has to add up to 0. So this needs to be a +10. Now, what does the iodine need to be to make that work out? Iodine would have to have an oxidation number of +5. So these are my actual answers. Copper is going to have an oxidation number of 2. Iodine is going to have an oxidation number of +5, and oxygen is going to have an oxidation number of -2. Now, I picked some pretty complicated ones to put in here, but we're not always going to be dealing with big, crazy compounds like this. If you look at C, this is sulfuric acid. This one might be a little bit closer to things that we would be dealing with more often. So again, I've got hydrogen, I've got sulfur, and I've got oxygen. I've got 2 hydrogens, I've got 1 sulfur, I've got 4 oxygens. I think about my rules. Hydrogen always has an oxidation state of +1. So that's a total of +2 towards it. Sulfur, we don't have any rules about. Oxygen is usually a -2. So this is going to be a -8. Now again, overall, this does not have a charge. So overall, this should add up to be 0. So again, 2 plus something -8 adds up to 0. That should be a 6, which means that sulfur needs to have an oxidation state of +6. So overall, my oxidation numbers are +1, +6, and -2. So these oxidation numbers really only help us, like I said, if we are talking about changing oxidation states as a reaction occurs. So let's take a look down here at example number 2, and let's see if we can see how these oxidation numbers change. So I've got, let's give a little space up at the top. So in our rules, we said that any element that is hanging out by itself is going to have an oxidation number of 0. So here magnesium is by itself. It does not matter what the coefficients are. So it's got an oxidation state of 0. So does this silicon hanging out here on the products. Looking at the silicon tetrachloride, and then the magnesium chloride here. We don't have any rules about silicon chloride or magnesium in our rules. Our main rules are about oxygen and hydrogen. So when in doubt, we're going to have to go with some of our charges. So silicon doesn't have an ionic charge normally, but chlorine can. Chlorine has a charge of -1. So we're going to use that as our reference oxidation number. Now I've got 4 of those chlorines, each one with a -1. So the silicon would have to have an oxidation number of +4 to make that add up to be a total of 0. Notice that that whole term does not have any charge on it. Same thing with the magnesium chloride. Both magnesium and chlorine have normal ionic charges, so I'm just going to stick with those. Magnesium is usually a +2, chlorine is usually a -1. Those still also both add together to equal that overall neutral charge of the magnesium chloride. So then our oxidation number should add up to be 0. So if we look at what's going on, we need to look and see which elements changed oxidation numbers. So silicon went from a +4 to a 0. So that definitely changed. Chlorine went from a -1 to a -1. That didn't change. Magnesium went from a 0 to a +2. So that did change. So silicon going from a +4 to a 0. We need to figure out whether this has gained electrons or lost electrons. Now remember that electrons have a negative charge. So when we think about going from +4 to 0, we're going, did that become more negative or more positive? So in this case, that became more negative. Again, think about number line. It's not actually going negative, but it's going more towards the negative side. So that silicon, if it's becoming more negative, we are gaining electrons. So remember, Leo, the lion, goes grr. Gaining electrons means we are reduced. So we're going to say that the silicon in silicon chloride was reduced. And then again, chlorine didn't change. Sometimes you're going to come across things that don't change. That's totally fine. Magnesium went from a 0 to a +2. That's becoming more positive, which means we lost electrons. If we lose electrons, we are oxidized. So we say the magnesium in magnesium was oxidized. Oh my gosh, I can't write. Oxidized. Right. So we've identified which species was oxidized. We've identified which species was reduced. And then we want to write these out as two half reactions. Now, we don't need to be perfect with this yet. We're going to talk more about half reactions coming up later. But when we have oxidation and reduction, we can write those out as two separate reactions. So what is happening here is that we want to write one half reaction for the oxidation and one half reaction for the reduction. So first, let's do the silicon because we talked about that first. So silicon chloride went to silicon. We said that that was reduced, so we gained electrons. We went from +4 to 0, so that was a change in charge of 4, which means that we had to add 4 electrons to this reaction to make that happen. Now, it looks weird because it is not balanced, because we've got this chlorine sort of hanging out there. What's going on with that? Don't worry about that right now. We really just want to sort of keep track of these electrons, right? So then we had magnesium. And magnesium chloride contains the other part that it changed to. So again, we said that the magnesium was oxidized, which means it lost electrons. It went from a 0 to a +2. So it lost 2 electrons. So when we are reduced, when we gain electrons, those electrons show up on the reactant side. When we are oxidized, when we lose electrons, those electrons show up on the products side. We're going to do a lot of this practice in class. This is something that we really need to make sure that we understand strongly, a skill that we need to be able to handle throughout this entire chapter. So I'm going to stop this video here. Make sure you watch this before class so that you can jump right in and do some of this practice in class. Then in the next video, in the part 2, we're going to talk about how to handle this in chemical equations when we know the equation already, but maybe it's not balanced. So I will see you all in class, and I'll talk to you later. Bye.